It's happening again. Right now, as you're reading this, Earth is sliding toward its next ice age, not in some distant future. The process has already begun. Within the next few thousand years, maybe less, glaciers will start advancing from the poles. Ice sheets will creep across continents, sea levels will drop hundreds of feet, and everything about our world will change. If you're using these to fall asleep, that's literally why I make them. So subscribe maybe and tell me where you are and what time. I check comments and it's like Berlin at breakfast, Boston at bedtime, all at once. This isn't speculation. It's not a maybe or a possibility. It's a certainty written in ice cores, ocean sediments, and geological records going back millions of years. Earth freezes, then it thaws, then it freezes again, like clockwork. Every 100,000 years, give or take, our planet transforms into a frozen wasteland where ice sheets miles thick cover continents and civilization as we know it becomes impossible. But here's what nobody tells you. We're living in the exception, not the rule. For the last 2.6 million years, Earth's default state has been Ice Age. The warm period we're experiencing right now, this comfortable climate that allowed human civilization to flourish, it's the anomaly. It's a brief intermission between acts in a play that's been running for millions of years. And the really crazy part? Scientists only figured out why this happens in the last few decades. The answer involves orbital mechanics, astronomical cycles, ocean currents, atmospheric carbon dioxide, and feedback loops so complex they make your head spin. But once you understand it, once you see how all these pieces fit together, you realize we're watching one of the most incredible phenomena in the solar system play out on our own planet. So buckle up, because we're about to dive deep into one of Earth's greatest mysteries. We're going to trace the story of ice ages from their discovery to the cutting-edge science that finally explained them. We're going to explore the mechanisms that turn Earth into a frozen ball and then thaw it out again, and we're going to confront some uncomfortable truths about where we are in this cycle right now. By the end of this, you're going to see our planet in a completely different way. You're going to understand that the world we know, the climate we take for granted, is temporary. And you're going to appreciate just how remarkable it is that we exist during one of Earth's rare, warm intervals. The story begins in the Swiss Alps in the early 1800s. A young naturalist named Louis Agassiz was studying something that puzzled him deeply. He kept finding these enormous boulders sitting in places they had no business being. Massive rocks weighing hundreds of tons perched on mountainsides miles from any source that could have produced them. The local people called them erratic rocks, and they had all sorts of folklore about how they got there. Giants threw them, floods carried them, the devil placed them there to confuse travelers. But Agassiz was a scientist. He needed a better explanation, and as he studied these boulders more carefully, examining the scratches and grooves carved into the bedrock beneath them, comparing them to similar features he'd seen near active glaciers, a wild idea started forming in his mind. What if these boulders had been carried here by ice? What if the glaciers that now clung to the highest peaks had once been much larger, extending far down into the valleys? What if all of Switzerland had once been covered in ice? It was a radical suggestion. The year was 1837, and the scientific establishment believed that Earth's climate had been essentially stable since creation. The idea that the planet's temperature could change dramatically, that ice sheets could grow and shrink, covering and uncovering vast areas. It seemed absurd. Agassiz presented his theory to the Swiss Society of Natural Sciences. The reception was hostile. His mentor, the respected naturalist Alexander von Humboldt, told him he was damaging his reputation by pursuing such a bizarre idea. Other scientists suggested the boulders had been carried by Noah's flood, which was still considered a legitimate geological explanation in the 1830s. But Agassiz was convinced. He spent the next several years travelling across Europe, documenting evidence of past glaciation, scratched bedrock, U-shaped valleys, moraines of debris left behind by retreating ice. Everywhere he looked, he found fingerprints of massive, ancient ice sheets. Slowly, grudgingly, the scientific community began to accept that Agassiz was onto something. By the 1860s, the Ice Age theory was becoming mainstream. Scientists started finding evidence of glaciation across North America, Scandinavia, and other parts of the world. The picture that emerged was stunning in its implications. At some point in the relatively recent past, geologically speaking, ice sheets thousands of feet thick had covered most of North America, Northern Europe, and parts of Asia. These weren't mountain glaciers, they were continental ice sheets comparable to what currently covers Antarctica. The Laurentide ice sheet that covered Canada and the northern United States was larger than Antarctica's ice sheet is today. It was so massive that its weight actually depressed the Earth's crust underneath it, pushing the land surface down hundreds of feet. But as researchers dug deeper, they discovered something even more remarkable. There hadn't been just one ice age. There had been multiple ice ages. The geological record showed evidence of several periods of glaciation separated by warmer intervals. This raised an obvious question. What could cause Earth's climate to swing so dramatically between frozen and warm states? What mechanism could plunge the planet into an ice age, hold it there for tens of thousands of years, then suddenly release it into a warm period? For decades, scientists proposed theory after theory. Maybe volcanic eruptions blocked sunlight, triggering cooling. Maybe changes in ocean currents redistributed heat differently. Maybe variations in atmospheric composition altered the greenhouse effect. Maybe the position of continents affected ice formation. All of these ideas had merit. Some of them were partially correct, but none of them could explain the timing. Because as scientists developed better methods for dating ancient ice and sediments, they discovered something that demanded explanation. The ice ages weren't random. They followed a pattern, a roughly predictable cycle that repeated over and over. And the dominant cycle, the one that controlled the major glaciations, had a period of approximately 100,000 years. This was baffling. What natural mechanism could produce such a precisely timed cycle? What could act like a metronome, ticking away for 100,000 years between major ice ages? The answer would come from an unlikely source. Not from a geologist or climate scientist, but from a mathematician and astronomer who was interested in the mechanics of planetary orbits. His name was Milutin Milankovitch, and in the early 1900s he became obsessed with a question that would consume decades of his life. Could variations in Earth's orbit around the Sun explain the Ice Age cycles? Now, most people think of Earth's orbit as stable and unchanging. We travel around the Sun in a nice circular path, spinning on our axis as we go, maintaining a consistent distance and orientation. But that's not quite accurate. Earth's orbit isn't perfectly circular. It's slightly elliptical, meaning we're closer to the Sun at some points in our orbit and farther away at others. More importantly, the shape of that ellipse changes over time. Sometimes Earth's orbit is more circular, and sometimes it's more stretched out. This variation is caused by gravitational interactions with other planets, primarily Jupiter and Saturn. Their massive gravitational fields tug on Earth as we all orbit the Sun, gradually altering the shape of our orbit over very long time periods. Milankovitch calculated that Earth's orbital eccentricity, the measure of how elliptical the orbit is, varies on a cycle of about 100,000 years and a longer cycle of about 400,000 years. When the orbit is more circular, the difference between Earth's closest and farthest approaches to the Sun is minimal. When the orbit is more elliptical, that difference becomes significant. But that wasn't all. Milankovitch discovered that Earth's axial tilt also changes over time. Right now, our planet is tilted at about 23.5 degrees relative to our orbital plane. But that tilt varies between about 22.1 and 24.5 degrees over a cycle of roughly 41,000 years. Why does this matter? Because Earth's axial tilt determines the intensity of seasons. When the tilt is greater, summers are hotter and winters are colder. When the tilt is smaller, seasons are more moderate. This affects how much ice can accumulate at high latitudes during winter and how much melts during summer. And there was a third factor. Earth's axis doesn't just tilt, it wobbles. Like a spinning top that's starting to slow down, our planet's rotational axis traces out a slow circle over time. This wobble, called precession, has a period of about 26,000 years. It affects which hemisphere is tilted toward the Sun during different parts of Earth's orbit, altering the timing and intensity of seasons. Milankovitch realized that these three cycles, orbital eccentricity, axial tilt, and precession, could combine in complex ways to alter the amount and distribution of solar radiation reaching different parts of Earth's surface. He spent decades performing incredibly complex calculations by hand, working out exactly how much sunlight would reach various latitudes during different seasons as these orbital parameters changed. The results were stunning. Milankovitch predicted that when these cycles aligned in certain ways, northern hemisphere summers would become cooler. And cooler summers, he argued, were the key to Ice Age formation. Not colder winters, but cooler summers. Here's why. Ice sheets don't grow because of exceptionally cold winters. They grow because summer isn't warm enough to melt all the snow that fell during winter. If you have cool summers that fail to melt the previous winter's snowfall year after year, decade after decade, that snow accumulates. It compresses into ice. It starts reflecting more sunlight, which cools the region further, which allows even more ice to accumulate. It's a feedback loop. More ice means more reflection of sunlight, which means cooler temperatures, which means more ice. Once you get it started, ice sheets can grow rapidly, expanding from high latitudes toward the equator, covering more and more of the planet's surface. Milankovitch published his theory in the 1920s and 1930s. It was mathematically elegant and physically plausible, but there was a problem. He had no way to test it. The climate records available at the time weren't precise enough to verify whether past ice ages really did correspond to his predicted orbital cycles. For decades, Milankovitch's theory languished in scientific limbo. Some researchers found it intriguing, others dismissed it as overly complex and unproven. The debate continued without resolution because nobody had the data to settle the question definitively. That changed in the 1970s when scientists developed new techniques for extracting and analyzing climate records from deep-sea sediments and ice cores. For the first time in history, researchers could reconstruct Earth's climate history with precision going back hundreds of thousands of years. What they found was remarkable. The climate record showed clear cyclical patterns. Periods of glaciation followed by warm interglacial periods, repeating over and over. And when scientists analysed the timing of these cycles, they found something that sent shockwaves through the scientific community. The cycles matched Milankovitch's predictions almost perfectly. There was a strong 100,000-year cycle corresponding to orbital eccentricity. There was a 41,000-year cycle corresponding to axial tilt variations. There was a 23,000-year cycle corresponding to precession. Milankovitch had been right. Earth's orbital variations were driving ice age cycles. The mathematics that he had worked out by hand decades earlier, before computers, before modern climate science, before anyone could actually verify his predictions, it was all correct. But here's where the story gets even more interesting. Because while Milankovitch's orbital cycles explained the timing of ice ages, they didn't explain the magnitude. The changes in solar radiation caused by orbital variations are actually quite small, only about 0.1% variation in the total amount of sunlight reaching Earth. That tiny change in incoming sunlight shouldn't be enough to trigger massive ice sheets that cover entire continents. Something else had to be amplifying the signal, taking those small orbital nudges and transforming them into dramatic climate swings. Scientists realized they were looking at a system of feedback loops far more complex than anyone had imagined. The orbital cycles were the pacemaker, the metronome that set the timing, but other factors were the amplifiers that transformed those subtle timing cues into full-blown ice ages and warm periods. One of the most important amplifiers turned out to be carbon dioxide. When researchers analysed air bubbles trapped in ancient ice cores, they made a stunning discovery. Carbon dioxide levels in the atmosphere were dramatically different during ice ages compared to warm periods. During glacial periods, CO2 levels dropped to about 180 parts per million. During warm interglacial periods like the present, they rose to about 280 parts per million. This correlation was nearly perfect. Every ice age showed low CO2 levels. Every warm period showed high CO2 levels. The atmospheric carbon dioxide was acting like a thermostat, amplifying and extending the climate changes triggered by orbital variations. But here's the puzzle that kept scientists up at night. Which came first? Did orbital changes cause ice to form, which somehow reduced atmospheric CO2, which then amplified the cooling? Or did CO2 change first, triggering ice formation, with orbital cycles just affecting the timing? The answer turned out to be both. It's a feedback loop where orbital changes initiate the process, but CO2 changes amplify and extend it, which triggers other feedbacks that affect CO2 levels further, creating a complex dance between astronomy, ocean chemistry, atmospheric composition, ice sheet dynamics, and biological processes. Let me break down how this actually works, because it's one of the most beautiful examples of of Earth system science, showing how different components of our planet interact in intricate ways. It starts with orbital cycles. When Earth's orbital configuration creates cooler northern hemisphere summers, snow that falls during winter doesn't completely melt. Over decades and centuries, this snow accumulates, particularly in high-latitude regions like Canada, Scandinavia, and Siberia. As snow accumulates and compresses into ice, it creates the first feedback loop. Ice and snow are highly reflective. Scientists call this property albedo. Fresh snow can reflect up to 90% of incoming sunlight back into space. This means that as ice sheets grow, they reflect more and more solar energy away from Earth's surface, causing additional cooling that allows ice sheets to expand even further. This is called the ice albedo feedback, and it's incredibly powerful. Once ice sheets start growing, they create conditions that accelerate their own growth. The more ice you have, the more sunlight gets reflected, the cooler it gets, the more ice you can support. But ice sheets don't just reflect sunlight, they also affect atmospheric circulation patterns. When you have massive ice sheets covering North America and Europe, you're essentially creating new mountain ranges made of ice, thousands of feet tall. These ice mountains alter wind patterns, change storm tracks, and affect precipitation distribution across the planet. The atmospheric changes affect ocean circulation. Winds drive ocean currents, and when wind patterns change, ocean circulation patterns change too. This is crucial because oceans are Earth's primary heat distribution system. They move enormous amounts of heat from equatorial regions toward the poles, moderating global temperatures. During ice ages, changes in ocean circulation alter how heat is distributed around the planet. The Gulf Stream, which currently brings warm water from the tropical Atlantic toward northern Europe, keeping places like England much warmer than they would otherwise be, this current system can weaken or shift position during glacial periods. But the really important ocean change involves what scientists call the biological pump. Oceans contain phytoplankton, microscopic plants that photosynthesize just like land plants, consuming CO2 from the atmosphere and producing oxygen. When these organisms die, they sink to the deep ocean, taking their carbon with them. During ice ages, changes in ocean circulation and chemistry affect phytoplankton productivity. In some regions, increased nutrient availability stimulates more phytoplankton growth, which pulls more CO2 out of the atmosphere. The carbon gets locked away in the deep ocean for thousands of years. At the same time, colder ocean water can absorb more dissolved CO2 than warm water. It's basic chemistry. Gases are more soluble in cold liquids than warm ones. So as oceans cool during glacial periods, they literally suck more CO2 out of the atmosphere and store it in the deep water. Sea ice formation also plays a role. When seawater freezes, it forms relatively pure ice, leaving salt behind. This creates dense, salty water that sinks to the ocean floor, driving deep water circulation. Changes in sea ice formation affect these deep water currents, which affects how carbon is distributed between surface waters and the deep ocean. The result of all these ocean processes is that atmospheric CO2 levels drop during glacial periods. This CO2 reduction amplifies the cooling initiated by orbital cycles. Carbon dioxide is a greenhouse gas. It traps heat in the atmosphere. When CO2 levels drop, less heat gets trapped, allowing the planet to cool further, which allows ice sheets to grow larger, which causes more cooling, which reduces CO2 levels more. It's feedback loops within feedback loops, each one amplifying the initial signal from orbital variations. A small change in summer sunlight caused by Earth's orbital configuration gets transformed into a massive climate shift because of these interconnected amplification mechanisms. But here's what really blows my mind. The system has brakes as well as accelerators. While ice sheets are growing and CO2 is dropping and the planet is cooling, other processes are working to eventually reverse the trend. Ice sheets grow by accumulating snow, but they also lose ice through melting and calving of icebergs. As ice sheets grow larger and extend into warmer regions, they become more vulnerable to melting. Eventually, ice loss can start to balance ice accumulation, stabilizing the ice sheets at their maximum extent. At the same time, volcanic eruptions continue throughout glacial periods, releasing CO2 into the atmosphere. Unlike the biological and ocean processes that remove CO2, volcanism doesn't stop during ice ages. Over tens of thousands of years, volcanic CO2 slowly accumulates in the atmosphere, even while other processes are trying to remove it. Eventually, orbital cycles shift again. Earth's orbital configuration changes to one that delivers more summer sunlight to northern high latitudes. Those slightly warmer summers start melting more ice than accumulates during winter. Ice sheets begin retreating. As ice sheets shrink, the ice albedo feedback runs in reverse. Less ice means less reflection of sunlight, which means more solar energy absorbed by Earth's surface, which means more warming, which causes more ice to melt. The feedback accelerates the deglaciation process. Retreating ice sheets expose land that had been covered for thousands of years. This newly exposed land is often dark-coloured rock and soil, which absorbs far more sunlight than the white ice it replaces. This further amplifies warming. As the planet warms, oceans warm too. Warm water releases dissolved CO2 into the atmosphere, just like a warm soda releases its fizz faster than a cold one. The biological pump changes as ocean circulation patterns shift. Nutrients become more or less available in different regions, affecting phytoplankton productivity and carbon uptake. Rising CO2 levels amplify the warming initiated by increased summer sunlight. More greenhouse gases mean more heat trapping, which means faster ice sheet melting, which means more CO2 release from warming oceans. Within a remarkably short time period, geologically speaking, the planet transitions from full glacial conditions to interglacial warmth. Ice sheets that took 90,000 years to build up can melt and retreat in just 10,000 years. The deglaciation process is much faster than the glaciation process. And then the planet reaches an interglacial period like the one we're in now. The Holocene, our current interglacial, began about 11,700 years ago when the last ice age ended. Ice sheets retreated to Greenland and Antarctica. Sea levels rose as meltwater flowed into the oceans. CO2 levels increased to about 280 parts per million. Global temperatures warmed to approximately current levels. But here's the thing that should keep you up at night. Interglacial periods don't last. They're temporary breaks in the Ice Age cycle. Based on the pattern of the last 800,000 years, interglacials typically last about 10,000 to 15,000 years. The Holocene is already 11,700 years old. By natural cycles, we should be approaching the end of this warm period. In fact, orbital parameters are already starting to shift in ways that would normally initiate the next glaciation. Northern Hemisphere summer insolation, the amount of sunlight reaching high northern latitudes during summer, has been declining for thousands of years. By Milankovitch theory alone, we should be seeing the first signs of ice sheet growth, except we're not. Instead, the planet is warming rapidly. Global temperatures are rising faster than at any time in the past several thousand years. Ice sheets are losing mass rather than gaining it. Sea levels are rising rather than falling. Why? Because humans have disrupted the cycle by adding massive amounts of CO2 to the atmosphere through fossil fuel burning. We've taken atmospheric CO2 from the natural interglacial level of 280 parts per million to over 420 parts per million today, a level not seen in millions of years. This extra CO2 is overwhelming the natural orbital forcing that would normally be nudging us toward the next ice age. Instead of cooling, we're warming. Instead of ice sheets starting to grow, they're shrinking. We've essentially postponed the next ice age, possibly for tens of thousands of years, depending on how much more CO2 we add to the atmosphere. Some people might think that sounds like a good thing. Who wants an ice age, right? Better to be warm than frozen. But the problem is, we've built our entire civilization during this interglacial period. Our cities, our agriculture, our infrastructure, all of it is optimized for the climate conditions that have existed for the past several thousand years. Rapid warming disrupts those conditions in ways that are extremely challenging to deal with. Rising sea levels threaten coastal cities. Changing precipitation patterns affect agriculture. More intense heat waves, storms and droughts stress infrastructure and ecosystems. We're conducting an unprecedented experiment with Earth's climate system, pushing it in directions it hasn't gone in millions of years. But to really understand the significance of what we're doing, we need to look at the longer history of ice ages on Earth. Because the 100,000 year cycle we've been discussing, that's actually a relatively recent phenomenon. For most of the past 2.6 million years, ice age cycles followed a different pattern. Going back in the geological record, scientists find evidence that ice ages have been occurring on and off for at least 2.6 million years. This period is called the Quaternary Ice Age, and we're still in it technically. The Quaternary Ice Age consists of alternating glacial and interglacial periods, with ice permanently present somewhere on Earth, either in continental ice sheets during glacials or restricted to polar regions during interglacials. But here's something fascinating. For roughly the first half of the Quaternary Ice Age, from 2.6 million years ago until about 1 million years ago, ice age cycles followed a different pattern than the 100,000 year cycle we see more recently. During this earlier period, the dominant cycle was about 41,000 years, matching Earth's axial tilt variations. Every 41,000 years, more or less, the planet would enter a glacial period, build up ice sheets, then melt them again. These glacial periods were generally less intense than the more recent ones. Ice sheets didn't grow quite as large. Sea levels didn't drop quite as much. The swings between glacial and interglacial conditions were more moderate. Then, around 1 million years ago, something changed. Scientists call it the mid-Pleistocene transition. Over a period of several 100,000 years, the dominant Ice Age cycle shifted from 41,000 years to 100,000 years. At the same time, ice ages became more severe. Ice sheets grew much larger, sea levels dropped much more, and the climate swings between glacial and interglacial conditions became more extreme. This transition has puzzled scientists for decades. Why would the climate system suddenly shift from responding primarily to axial tilt variations to responding primarily to orbital eccentricity? The orbital cycles didn't change. Earth's tilt still varies on a 41,000-year cycle. Earth's orbital shape still varies on 100,000 and 400,000-year cycles. Those astronomical forcings remained constant, so something about Earth itself must have changed, altering how the planet responded to orbital forcing. But what? Several theories have been proposed. One suggests that gradual cooling over millions of years eventually reached a threshold where ice sheets could grow large enough to persist through multiple orbital cycles, creating longer-lasting glacial periods. Another theory focuses on changes in atmospheric CO2. Some researchers believe that CO2 levels gradually declined over the past few million years, making the planet more sensitive to orbital forcing and allowing ice sheets to grow larger during glacial periods. A third idea involves changes in ocean circulation. The development of modern ocean current systems, particularly the thermohaline circulation that drives deep water formation in the North Atlantic, may have altered how Earth responds to orbital variations. Yet another theory suggests that erosion of mountain ranges and changes in continental configuration affected atmospheric and ocean circulation patterns in ways that amplified Ice Age cycles. The honest answer is that scientists still don't fully understand why the mid-Pleistocene transition occurred. It's an active area of research, with new data and theories emerging regularly. But what's clear is that Earth's climate system can undergo fundamental shifts in its behavior, even while external forcings remain constant. This has important implications for understanding current climate change. It shows that climate doesn't just respond linearly to forcings. There can be threshold effects, tipping points, and regime shifts where the system suddenly starts behaving differently. It also shows that the 100,000-year cycle we've been discussing isn't necessarily a permanent feature of Earth's climate. It emerged relatively recently in geological terms and could potentially shift again in the future. But let's get back to the mechanics of these 100,000-year cycles, because there are still some fascinating details we haven't covered. One of the most intriguing aspects is how different parts of the world respond to glacial interglacial cycles. You might think that ice ages affect the whole planet uniformly. Everything gets colder during glacials, everything gets warmer during interglacials, but that's not actually true. The climate changes during glacial cycles are highly regional, with some areas experiencing dramatic shifts, while others remain relatively stable. The most obvious regional differences involve ice sheets themselves. During glacial periods, massive ice sheets cover North America and Eurasia, but they're largely absent from the Southern Hemisphere. Antarctica has permanent ice sheets that grow larger during glacials, but South America, Southern Africa, and Australia don't develop comparable ice coverage. This asymmetry is caused by the distribution of land masses. The The northern hemisphere has large continental areas at high latitudes where ice sheets can form and grow. The southern hemisphere has much less land at high latitudes, mostly just Antarctica, which is already covered in ice. But the regional differences go beyond just ice sheet coverage. Climate patterns, precipitation, temperature changes, ecosystem shifts, all of these vary dramatically from region to region during glacial cycles. Take Africa, for example. During glacial periods, much of Africa became drier. The Sahara Desert expanded significantly. Many of the Great Lakes of East Africa shrank or dried up completely. Tropical rainforests retreated to small refugia. These environmental changes had profound effects on human evolution, as we discussed earlier, creating selection pressures that shaped our species. But at the same time, some regions of Africa actually became wetter during glacial periods. Southwestern Africa, for instance, received more rainfall during some glacial cycles. The regional climate patterns were complex and didn't follow simple colder equals drier relationships. Australia provides another fascinating example. During glacial periods, Australia was generally drier, and many of its inland lakes dried up. But the continental shelf that's currently underwater was exposed, creating vast new areas of habitable land. Australia, New Guinea and Tasmania were connected into a single landmass called Sahul, and early humans were able to walk between them. In Southeast Asia, lower sea levels exposed the Sunda Shelf, connecting what are now islands into a large peninsula. You could walk from mainland Southeast Asia to Borneo, Java, and Sumatra. This dramatically changed migration patterns for both humans and animals. The Amazon rainforest, one of the most biodiverse ecosystems on Earth, also went through dramatic changes during glacial cycles. Some researchers believe the rainforest fragmented into isolated patches during the driest glacial periods, with savanna and grassland replacing much of the forest. These forest refugia became centers of speciation, where isolated populations evolved into new species, contributing to the Amazon's incredible biodiversity. But other evidence suggests the Amazon remained mostly intact, even during glacial periods, just shifted in composition with different tree species dominating than today. The debate continues, but either way, it's clear that glacial cycles dramatically affected tropical as well as polar regions. Ocean circulation patterns also shifted during glacial periods in complex ways. The Gulf Stream and North Atlantic Current, which currently bring warm water northward and help moderate European climate, weakened during glacials. This contributed to the severe cold experienced by Europe during ice ages. The Antarctic Circumpolar Current, the powerful current that circles Antarctica, may have changed position and strength during glacial cycles, affecting heat distribution throughout the southern hemisphere oceans. Deep water formation, the process where dense, cold water sinks to the ocean floor and drives global circulation patterns, shifted location and intensity during glacial periods. This affected nutrient distribution, biological productivity, and carbon storage in the oceans. Some researchers have found evidence of abrupt climate changes during glacial periods where ocean circulation patterns suddenly shifted, causing rapid temperature swings within just a few decades. These events, called Dansgaard-Oeschger events, occurred repeatedly during the last ice age, causing temperature changes of up to 15 degrees Celsius in Greenland within a human lifetime. These abrupt changes weren't just limited to polar regions. They affected weather patterns worldwide, altering monsoon intensity in Asia, rainfall in South America, and temperature in Antarctica. The climate system during glacial periods was highly unstable, prone to sudden shifts that must have been terrifying for our ancestors living through them. Ecosystems responded to these glacial cycles in complex ways. During glacial periods, many species shifted their ranges toward the equator, following their preferred climate conditions. Temperate forests that now grow across Canada and northern Europe retreated to southern refugia. Arctic tundra expanded to cover areas that are now heavily forested. But species didn't just shift uniformly. Migration routes were blocked by ice sheets, mountain ranges, and changed ocean levels. Some populations became isolated, leading to speciation events. Other populations went extinct when their habitats disappeared. The distribution of species we see today is largely a result of these glacial-interglacial migrations and adaptations. Large mammals were particularly affected. During glacial periods, megafauna like mammoths, mastodons, giant ground sloths, saber-toothed cats, and cave bears thrived in Ice Age environments. These animals were adapted to cold conditions and the ecosystems that existed during glacials. When the climate warmed and entered interglacial periods, many of these species went extinct. The combination of rapidly changing climate and human hunting pressure proved too much for them. The end of the last ice age, about 11,000 years ago, saw the extinction of dozens of large mammal species worldwide. Plants also showed complex responses. During glacial periods, CO2 levels dropped to around 180 parts per million, close to the minimum level needed for C3 photosynthesis, the type most plants use. This CO2 starvation stressed plant communities and may have contributed to the expansion of grasslands at the expense of forests, since grasses use a more efficient photosynthetic pathway that works better at low CO2 levels. When interglacial periods began and CO2 levels rose, plants responded with increased growth and productivity. Forests expanded, grasslands retreated, the distribution of biomes shifted dramatically within just a few thousand years. These ecosystem changes created complex challenges and opportunities for early humans. Ice Age environments were very different from today's world, with different plants and animals, different resource distributions, and different hazards. Humans had to be incredibly adaptable to survive through these changes. They needed to adjust their diets as plant and animal communities shifted. They needed to develop new hunting and gathering strategies as familiar species disappeared and new ones appeared. They needed to migrate as ice sheets advanced or retreated, always searching for habitable regions with adequate resources. The humans who survived weren't necessarily the strongest or the smartest in an abstract sense. They were the most flexible, the most capable of learning and adapting to new conditions, the most successful at cooperating to solve novel problems. This adaptability, forged by hundreds of thousands of years of climate instability, is part of what makes humans so successful today. We're generalists who can thrive in almost any environment because our ancestors had to be generalists to survive glacial, interglacial cycles. But here's something that should give us pause. All of human civilization, everything we think of as recorded history, has occurred during the current interglacial period. The Holocene has been remarkably stable compared to the wild climate swings of the last ice age. Temperatures have varied, but not dramatically. We haven't experienced abrupt Dansgaard-Oeschger events or sudden collapses of major ice sheets. This stability allowed agriculture to develop. You can't farm successfully if the climate is changing dramatically every few decades. You need predictable seasons, reliable rainfall patterns, and stable temperatures. The Holocene provided that stability for the first time in tens of thousands of years. Cities, civilizations, and complex societies all emerged during this stable period. The entire structure of modern civilization is built on the assumption that climate will remain relatively stable, that sea levels won't change dramatically, that rainfall patterns will stay consistent enough for agriculture to work. But we know from the geological record that this stability is temporary. Interglacial periods eventually end. Based purely on orbital cycles, the next glaciation should begin within the next few thousand years as summer sunlight in northern high latitudes continues to decline. Of course, human-caused global warming has probably delayed or prevented the next ice age by adding so much CO2 to the atmosphere. Some climate scientists estimate we may have postponed the next glaciation by 50,000 years or more. In a perverse way, global warming might be protecting us from the return of ice sheets. But this creates a new set of problems. We're pushing the climate system in the opposite direction from the natural orbital forcing, creating warmth at a time when we would naturally be cooling. This mismatch between natural cycles and human forcing is taking us into uncharted territory. The climate system is responding to two competing influences: orbital cycles trying to cool the planet and greenhouse gases trying to warm it. The outcome depends on the balance between these influences and how various feedback loops amplify or moderate them. We're running an experiment that's never been done before. We're taking a climate system that naturally oscillates between glacial and interglacial states on 100,000-year cycles and disrupting that oscillation by adding massive amounts of CO2 in just a few centuries. Nobody knows exactly what will happen. Climate models give us projections, but models are simplifications of reality. They might miss important feedbacks or tipping points. The climate system might respond in ways we haven't anticipated. What we do know is that we're moving into conditions Earth hasn't experienced in millions of years. CO2 levels above 400 parts per million haven't existed since the Pliocene, about 3 million years ago, when global temperatures were 2 to 3 degrees Celsius warmer than today and sea levels were 15 to 25 meters higher. If we continue increasing CO2 levels, we could eventually reach conditions not seen since the Eocene 50 million years ago, when Earth was so warm that palm trees grew in Alaska and there was essentially no permanent ice anywhere on the planet. These past warm periods took millions of years to develop and millions of years to end. But we're forcing similar changes in just centuries. The speed of change is unprecedented in the geological record, except for rare catastrophic events like asteroid impacts. This brings us to a fundamental question about the 100,000-year cycle. Is it a natural, inevitable feature of Earth's climate system that will continue indefinitely? Or can it be disrupted by sufficiently large perturbations? The geological record suggests that ice age cycles can indeed be disrupted. Going back further in Earth's history, we find periods of millions of years when the planet had little or no ice anywhere. During the Cretaceous period, when dinosaurs roamed, Earth was much warmer than today, with no ice sheets at the poles and sea levels hundreds of feet higher than present. These ice-free or greenhouse periods lasted for tens of millions of years before plate tectonics, ocean circulation changes, and declining CO2 levels gradually cooled the planet enough for ice to return. The Quaternary Ice Age we're currently in, with its alternating glacial and interglacial periods, is actually unusual from a deep time perspective. For most of Earth's history over the past 500 million years, the planet has been warmer than today, with no permanent ice sheets. The Ice Age cycles we've been discussing are relatively recent phenomena that only became important in the last few million years. So Earth's climate system has multiple stable states. It can exist as an ice-free greenhouse world. It can exist in an Ice Age state with permanent polar ice and oscillating glacial interglacial cycles. And it can exist in various intermediate states. What determines which state Earth occupies? Primarily atmospheric CO2 levels, which are controlled by the balance between volcanic outgassing, weathering of rocks, biological uptake, and ocean chemistry. On very long timescales, millions of years, plate tectonics affects these processes by changing the configuration of continents, the height of mountain ranges, and the patterns of ocean circulation. The current Ice Age state is probably a result of several factors coming together. The formation of the Himalayan mountain range increased weathering rates, removing CO2 from the atmosphere. The closing of tropical seaways by continental drift changed ocean circulation patterns. The position of Antarctica over the South Pole allowed ice sheets to form there, which changed planetary albedo and ocean circulation. These factors gradually cooled the planet over tens of millions of years until Ice Age cycles became possible. Once initiated, the cycles have persisted for 2.6 million years, governed by orbital variations that pace the advance and retreat of ice sheets. But this raises an important point. The 100,000-year cycle requires the planet to be in a particular climate state where orbital variations can trigger ice sheet growth and decay. If Earth gets too warm or too cold, the cycle breaks down. If Earth gets too warm, ice sheets can't grow during cool orbital phases. The planet stays in a permanent interglacial or enters an ice-free state. This is probably what we're doing now with anthropogenic warming. We're heating the planet enough that ice sheets won't be able to grow even when orbital cycles favor glaciation. If Earth gets too cold, ice sheets might never retreat completely. The planet could enter a snowball Earth state where ice extends all the way to the equator and stays there for millions of years. This happened several times in Earth's very distant past, most recently about 600 million years ago, but it requires much more extreme cooling than the Quaternary Ice Age cycles have produced. So the 100,000-year cycle exists in a Goldilocks zone of climate conditions. Not too warm, not too cold, just right for orbital variations to trigger major ice sheet oscillations. And human activities are pushing us out of that zone. The future of Earth's climate depends critically on what we do over the next few centuries. If we drastically reduce CO2 emissions and atmospheric levels eventually decline back toward natural interglacial values, the 100,000-year cycle might resume in tens of thousands of years. Orbital forcing would eventually overwhelm the temporary human perturbation. But if we continue adding CO2 and push atmospheric levels to 600, 800 or 1,000 parts per million, we could end the Quaternary Ice Age entirely. the planet might shift into a new stable state without glacial interglacial cycles, remaining warm for millions of years until plate tectonics and natural weathering processes gradually remove the excess CO2. This would be a fundamental change to Earth's climate system, comparable to the initiation of the current Ice Age 2.6 million years ago, or the mid-Pleistocene transition that shifted Ice Age cycles from 41,000 to 100,000 years. We would be responsible for altering a climate pattern that has governed Earth for millions of years. The weight of that responsibility is staggering. Our actions over the next few centuries will determine the climate trajectory of Earth for thousands or even millions of years into the future. We're not just affecting ourselves or our children, we're potentially affecting the entire future evolution of Earth's climate system. Understanding the 100,000-year cycle gives us context for appreciating both the natural climate variability of our planet and the unprecedented nature of current human-caused changes. It shows us that Earth's climate is always changing, driven by astronomical cycles, feedback loops, and complex interactions between ice, ocean, atmosphere, and life. But it also shows us that these natural changes occur on timescales of thousands to hundreds of thousands of years. The changes we're causing are happening in just decades to centuries, orders of magnitude faster than natural ice age cycles. The climate system we're disrupting is the same system that has shaped human evolution, migration, and adaptation for hundreds of thousands of years. It's the system that made us who we are as a species, and now we've become powerful enough to disrupt it. Looking back at the journey we've taken through Ice Age science, from Louis Agassiz's noticing erratic boulders in the Alps to modern climate scientists extracting ice cores from Antarctica and analysing ocean sediments, it's remarkable how far our understanding has come. We now know that Earth freezes every 100,000 years because of orbital variations discovered by Milankovitch, amplified by CO2 changes in the atmosphere and oceans, reinforced by ice albedo feedbacks, and modulated by complex interactions between climate components that scientists are still working to understand. We know that ice ages profoundly affect every aspect of Earth's surface, from sea level to ecosystem distribution to human evolution and migration. We know that the warm interglacial we're living in is temporary and should naturally end within the next few thousand years. And we know that human activities have disrupted this natural cycle in ways that will affect Earth's climate for thousands or millions of years into the future. The 100,000-year cycle is one of Earth's fundamental rhythms, like the daily rotation creating day and night, or the annual orbit creating seasons. For 2.6 million years, it has governed the advance and retreat of ice sheets, the rise and fall of sea level, and the expansion and contraction of habitable zones for plants, animals, and humans. Our ancestors lived through multiple complete cycles, adapting to glacial and interglacial conditions, developing the flexibility and intelligence that allowed them to thrive in changing environments. That adaptability is our inheritance from them. Now we face a different challenge, not adapting to natural climate cycles, but deciding whether to allow those cycles to continue or to fundamentally alter them through our actions. It's a choice that will define our species and our relationship with Earth for as long as humans exist. The next time you hear about climate change or global warming, remember the 100,000-year cycle. Remember that we're living in a temporary warm period between ice ages. Remember that our planet has been freezing and thawing in a regular rhythm for millions of years. And remember that we've become powerful enough to disrupt that ancient rhythm, for better or worse, forever changing Earth's climate trajectory. That's the real story behind why Earth freezes every 100,000 years. It's not just about ice sheets and orbital mechanics, it's about understanding our planet as a complex, dynamic system that operates on timescales far longer than human civilization. It's about recognizing that the stable climate we've enjoyed for the past 10,000 years is unusual and temporary. And it's about accepting the awesome responsibility that comes with being the first species capable of intentionally or unintentionally altering the fundamental climate patterns of an entire planet. The 100,000-year cycle will continue unless we stop it. The ice will return unless we prevent it. And the decisions we make now will echo through millennia, affecting not just our descendants, but the entire future evolution of Earth's climate system. That's the power we've gained through technology and the burden we must carry as a species. We are no longer just passengers on this planet, subject to its natural rhythms. We've become, for better or worse, one of the forces that shapes those rhythms, and that changes everything. But to really understand the full implications of the 100,000-year cycle and what it means for our future, we need to dig deeper into the mechanisms, explore the evidence in much more detail, and look at what actually happens during these transitions between glacial and interglacial states. Let's start by examining exactly what Earth looks like during a full glacial period, because most people have no idea just how dramatically different our planet becomes when the ice advances. Picture Earth 20,000 years ago at the peak of the last ice age. This period is called the last glacial maximum, and it represents the most recent time when ice sheets reach their greatest extent. If you could look at Earth from space, you'd barely recognize it as the same planet we live on today. The Laurentide ice sheet covers virtually all of Canada and extends deep into what is now the United States. Ice reaches as far south as New York City, covering the site where Manhattan will someday stand under thousands of feet of frozen water. The Great Lakes don't exist yet. They're buried under ice. The entire landscape from the Arctic Ocean to the Ohio River Valley is nothing but white, a vast frozen desert that seems to stretch forever. The ice isn't just a thin coating. In places, it's more than 2 miles thick. That's 10,000 feet of solid ice, weighing so much that it's actually pushing the Earth's crust down hundreds of feet, depressing the solid rock beneath it like a heavy weight pressing into soft clay. The sheer mass of these ice sheets is literally changing the shape of the planet. Across the Atlantic, the situation is similar. The Fennoscandian ice sheet covers Scandinavia, extending across what is now the Baltic Sea and pushing deep into northern Europe. Britain and Ireland are mostly covered. The ice reaches as far south as Berlin. Northern Russia is buried under glaciers. The Alps have their own ice cap, with glaciers extending far down into the valleys. The Pyrenees between France and Spain are heavily glaciated. Even the mountains of northern Africa have glaciers that don't exist today. But here's what's really mind-blowing. All this ice has to come from somewhere, and that somewhere is the ocean. When you lock up water in continental ice sheets, sea level drops. And during the last glacial maximum, sea level was about 400 feet lower than today. 400 feet. Let that sink in. A 40-story building worth of water just gone from the oceans, frozen on land instead. This completely changes the geography of the planet. The continental shelves, those shallow areas around the edges of continents that are currently underwater, they're completely exposed. The Atlantic coast of North America extends 100 miles or more beyond the current shoreline. You could walk from Long Island to the edge of the continental shelf, crossing dry land where fishing boats now sail in 200 feet of water. The English Channel doesn't exist. Britain is connected to continental Europe by a vast plain where the North Sea currently sits. You can walk from London to Amsterdam without getting your feet wet. The Thames and the Rhine are tributaries of a larger river system that flows across this exposed plain to the ocean edge, far to the north of the current coastline. The Bering Strait is dry land, a 1,000-mile-wide bridge connecting Asia to North America. Humans and animals can freely walk between continents. Alaska and Siberia are one continuous landmass called Beringia. In Southeast Asia, the Sunda Shelf is exposed, connecting Thailand, Malaysia, Sumatra, Java, and Borneo into a single enormous peninsula. Indonesia, as we know it, a nation of islands, doesn't exist. It's one massive extension of the Asian mainland. Australia, New Guinea, and Tasmania are joined into the supercontinent of Sahul, with vast plains connecting them across what is now the Arafura Sea and Torres Strait. The Mediterranean Sea is smaller, with many of its islands connected to the mainland. The Persian Gulf is dry land, a river valley where the Tigris and Euphrates flow to the ocean hundreds of miles south of the current shoreline. The geography of the glacial Earth is so different from today that it would be disorienting to modern humans. Coastlines are in completely different places. Major islands don't exist or are connected to continents. Shallow seas are dry land. The world map would need to be completely redrawn. But the changes aren't just about ice and sea level. The entire climate of the planet is different in ways that affect every ecosystem and every region. Global average temperature during the last glacial maximum was about 5 to 6 degrees Celsius cooler than today. That might not sound like much, but remember that this is a global average. Some regions were much colder than average, while a few tropical areas were only slightly cooler than today. The northern continents were absolutely frigid. Temperatures in Canada and northern Europe were 20 to 30 degrees Celsius colder than present. Winters were brutally cold, with temperatures regularly dropping below minus 40 degrees Celsius. Summers were short and cool, barely warm enough to melt the surface of the ice sheets. But it wasn't just the cold. The climate patterns were completely different. The jet stream, that river of fast-moving air in the upper atmosphere that steers weather systems, took a very different path. Instead of flowing relatively straight across the northern hemisphere at middle latitudes, it was deflected far to the south by the massive ice sheets. This meant that storm tracks were different. Precipitation patterns changed. Areas that are now wet were dry. Regions that are now dry received more rainfall. The monsoon systems of Asia and Africa were weaker or shifted in position. Europe, despite being much colder, was also much drier. The ice sheets blocked moisture from the Atlantic, creating cold desert conditions across much of the continent. The landscape looked more like modern Siberia than modern Europe, with sparse vegetation, frequent dust storms, and permafrost extending hundreds of miles south of the ice margin. North America experienced similar conditions. South of the ice sheets, a broad band of tundra extended across what is now the northern United States. This wasn't the lush forest landscape we know today. It was a treeless plain with low-growing shrubs, grasses, and wildflowers adapted to cold, dry conditions. Further south, forests did exist, but they were different from today's forests. Species compositions were unique, with combinations of plants that don't occur together in modern ecosystems. Trees that now live far apart geographically grew side by side because they were all seeking the same climate refugia. The tropics were cooler and generally drier. Rainforests retreated to smaller areas with reliable rainfall. Many tropical regions that are now forested were grassland or savanna. Lake levels across Africa, South America, and Australia were much lower than today. Some lakes dried up completely, but not all changes were toward drier conditions. Some regions actually received more precipitation during glacial periods. The southwestern United States, which is now mostly desert, had larger lakes and more vegetation during the last ice age. Places that are now dry lake beds in Nevada and Utah held deep lakes hundreds of feet deeper than they are today. The Sahara Desert went through cycles of expansion and contraction during glacial periods. At some points, it was even more extensive than today, pushing the savanna zones of Central Africa into narrow refugia. But at other times, shifts in the monsoon brought more rain to the Sahara, creating periods when it was much greener than present. These climate changes had profound effects on ecosystems and the animals living in them. The Ice Age world was home to a spectacular array of megafauna that are now extinct or greatly reduced in range. Woolly mammoths roamed across the tundra and grasslands of the northern continents. These weren't just elephants with fur. They were specifically adapted to Ice Age conditions, with small ears to minimize heat loss, a thick layer of insulating fat, and the ability to dig through snow to reach vegetation. Giant ground sloths, some as large as elephants, lived across North and South America. Saber-toothed cats hunted the grasslands. Giant short-faced bears, the largest land predators of the Ice Age, dominated North America. Cave lions and cave bears prowled Europe and Asia. Woolly rhinoceroses, giant deer with antlers spanning 12 feet, massive bison and countless other large mammals filled ecological niches that are now empty or occupied by much smaller species. The Americas were particularly rich in megafauna. North America had camels, horses, ground sloths, mammoths, mastodons, giant beavers the size of bears, armadillo-like glyptodonts the size of cars, and predators to match. Why did these animals thrive during ice ages but struggle or disappear during warm periods? Partly it's because they were specifically adapted to ice age conditions. Mammoths, for instance, were built for cold climates. Their thick fur, fat reserves, and physiological adaptations helped them survive brutal winters that would kill modern elephants. But it's also about the ecosystems. The cold, dry climate of glacial periods promoted extensive grasslands and tundra, which supported huge herds of grazing animals. These grazers could exist in densities that seem impossible today because the vegetation was constantly renewed by cold-adapted grasses that grew efficiently in the cool conditions. The mammoth steppe, as scientists call it, stretched from Spain to Canada in a nearly continuous band across the northern hemisphere. It was one of the most productive ecosystems ever to exist. supporting biomass densities that exceeded even the famous African savanna. This productivity supported predator populations that were equally impressive. The Ice Age landscape had predators around every corner: saber-toothed cats, dire wolves, short-faced bears, lions, hyenas. The competition was intense, and only the most successful hunters survived. Humans were part of this ecosystem, competing with other predators for prey, adapting their hunting strategies to Ice Age conditions, developing technologies that allowed them to kill megafauna and survive in environments that would kill unprotected humans in hours. The archaeological evidence from this period is absolutely fascinating. We find human sites across the ice-free portions of the northern continents, from France to Siberia to Alaska. These weren't primitive people barely surviving. They had sophisticated toolkits, elaborate shelters, art and music, and complex social organizations. They hunted mammoths using techniques that required careful planning and coordination. Archaeological sites show evidence of communal hunts where multiple families worked together to drive mammoths into kill zones, butcher them efficiently, and distribute the meat and other resources among the group. They made clothing from animal skins that was probably more effective at cold weather protection than anything available until modern synthetic materials. Archaeological finds include needles, suggesting they were sewing fitted garments rather than just wrapping themselves in hides. Fitted clothing with minimal air gaps is crucial for surviving extreme cold. They built substantial shelters, some using mammoth bones as structural elements when wood was scarce. These weren't crude huts. They were engineered structures with multiple rooms, storage areas, and sophisticated heating systems using carefully managed fires. They created art that rivals anything from later periods: cave paintings, carved figurines, decorated tools, and weapons. They made musical instruments, including those bone flutes we discussed earlier. They developed elaborate burial practices and what appears to be spiritual or religious belief systems. In other words, they were fully modern humans, mentally and culturally, living during the last glacial maximum. They had the same brains we do, the same cognitive abilities, the same capacity for language, planning, and abstract thought. But they were living in a world so different from ours that it might as well be an alien planet, and they were thriving in conditions that would defeat most modern humans within days or weeks. Now here's what really makes you appreciate the Ice Age cycle. This glacial world, as harsh and strange as it seems to us, wasn't a brief aberration. It was the norm for roughly 90,000 of every 100,000-year cycle. Earth exists in glacial or near-glacial conditions. The warm interglacial periods, like the one we're in now, they're the brief exceptions. Our comfortable modern climate is the anomaly. The frozen world is the default state. This has profound implications for understanding human evolution and history. For most of the past few 100,000 years, our ancestors lived in Ice Age conditions. The warm interglacial periods were brief respites between long glacial periods. Modern humans, Homo sapiens, evolved during a glacial period. Our species emerged sometime between 300,000 and 200,000 years ago in Africa, during a time when ice sheets covered much of the northern continents and the climate was generally cooler and drier than today. We spread out of Africa during glacial periods, migrating into Europe and Asia when sea levels were low and land bridges were exposed. We reached Australia during a glacial period, crossing ocean barriers that are now wider. We entered the Americas via the Bering Land Bridge during the last glacial period. Essentially, most of human evolution and migration occurred during ice ages, not during warm periods. We're an ice age species that happens to be living during a warm interglacial. This raises interesting questions about human adaptability. We evolved to handle ice age conditions. Our physiology, our behavior, our cognitive abilities were all shaped by the challenges of glacial climates. Are we equally well adapted to warm climates, or are we actually better suited to cooler conditions? Some researchers argue that humans are fundamentally Ice Age animals. Our ability to survive in cold climates with relatively little natural protection, our high metabolism that generates lots of body heat, our capacity for complex planning and cooperation that was essential for Ice Age survival, these are all Ice Age adaptations. But humans have also proven remarkably adaptable to warm climates. Indigenous peoples of tropical regions have thrived for thousands of years. Human populations exist successfully everywhere, from the Arctic to the equator. This adaptability, this ability to survive and thrive in almost any climate Earth can produce, is perhaps our species' greatest strength. We're not tied to one specific environment or climate. We can handle the frozen wastes of Ice Age tundra and the steamy heat of tropical rainforests with equal success. But let's get back to the Ice Age cycle itself, because we need to understand what happens during the transitions between glacial and interglacial states. These transitions are the most dramatic climate changes Earth experiences, and they reveal a lot about how the climate system works. The transition from glacial to interglacial, called deglaciation or termination, is particularly fascinating because it happens relatively quickly. Ice sheets that took 80,000 to 90,000 years to build up can melt and retreat in just 10,000 to 20,000 years. The warming is rapid and dramatic. What triggers this transition? Remember Milankovitch cycles. When Earth's orbital configuration shifts to one that delivers more summer sunlight to northern high latitudes, summers become warm enough to start melting more ice than accumulates during winter. At first, the changes are subtle. Maybe a few extra feet of ice melt each summer. The ice sheets are still massive, still growing in some areas, even as they start retreating in others. But the balance has shifted. More ice is melting than is being added. As ice sheets start shrinking, several feedback loops kick in that accelerate the process. The ice albedo feedback runs in reverse. Less ice means less reflection of sunlight, which means more solar energy absorbed by Earth's surface, which means more warming, which means more ice melting. Retreating ice exposes dark rock and soil that absorbs far more sunlight than white ice. This dramatically increases local warming. Areas that were under ice for tens of thousands of years suddenly receive full sunlight on dark surfaces. The temperature change can be dramatic. As glaciers retreat, they often leave behind large lakes of meltwater. These glacial lakes can cover thousands of square miles. The water is dark and absorbs sunlight, further warming the region. Some of these glacial lakes were enormous. Lake Agassiz, which formed from melting ice in North America, was larger than all the current Great Lakes combined. These meltwater lakes don't just sit there. They affect local and regional climate, altering precipitation patterns and temperature gradients, and sometimes, catastrophically, they drain. When ice sheets retreat, they can block river drainage, creating huge lakes behind ice dams. If those ice dams fail suddenly, the resulting flood can be catastrophic. Millions of cubic meters of water can be released in days or hours, carving massive channels in the landscape and delivering enormous volumes of fresh water to the oceans. These glacial lake outburst floods have happened repeatedly during deglaciations. The channeled scablands in Washington state were carved by repeated catastrophic floods. When Lake Missoula, a huge glacial lake, broke through its ice dam and drained in a matter of days. The landscape still bears the scars of these floods thousands of years later. These meltwater pulses affect more than just local landscapes. When huge volumes of fresh water enter the ocean, they can disrupt ocean circulation patterns. Remember that ocean circulation is driven partly by density differences. Cold, salty water is dense and sinks to drive deep water currents, but fresh meltwater is less dense than salt water. When enormous amounts of fresh water pour into the North Atlantic, it can create a lens of less dense water floating on top of the ocean, preventing normal deep water formation. This can slow or shut down the Atlantic meridional overturning circulation, the system that includes the Gulf Stream. When this circulation slows or stops, it has dramatic climate effects. Europe loses its primary heat source. Temperatures drop, sometimes very rapidly. These events have been documented repeatedly during the last deglaciation. They're called Heinrich events, after the scientist who first described them, and they caused rapid cooling in the midst of overall warming trends. So the transition from glacial to interglacial isn't smooth. It's punctuated by rapid changes, reversals, and abrupt shifts. The climate system during deglaciations is highly unstable, prone to sudden jumps between different states. One of the most famous examples is the Younger Dryas event, which occurred about 12,800 years ago. Earth was warming rapidly, ice sheets were retreating, and the last ice age seemed to be ending. Then, suddenly, temperatures plunged back toward glacial conditions. In less than a decade, the climate in the North Atlantic region cooled by several degrees. Ice sheets that had been retreating started advancing again. This cold snap lasted about 1,200 years. Then, just as suddenly as it began, it ended. Temperatures shot up, in some regions rising 10 degrees Celsius in just a few decades. The deglaciation resumed. Ice sheets continued retreating, and the current interglacial period, the Holocene, truly began. What caused the Younger Dryas? The most widely accepted theory involves meltwater from the North American ice sheet. As the Laurentide ice sheet retreated, it released enormous amounts of meltwater. Initially, this water drained south through the Mississippi River system into the Gulf of Mexico. But as ice continued melting, new drainage routes opened. Suddenly, the meltwater found a new path through the St. Lawrence River Valley directly into the North Atlantic. Massive volumes of fresh water poured into the North Atlantic in a geologically brief period, disrupting ocean circulation and triggering rapid cooling. The Younger Dryas shows us how sensitive the climate system can be during transitions. Small changes, like the opening of a new meltwater drainage route, can trigger large climate responses that affect the entire planet. It also shows us how quickly climate can change. A decade to plunge into cold conditions, a few decades to warm up again. These aren't gradual shifts occurring over thousands of years. These are abrupt changes that happen within a human lifetime. Our ancestors lived through the Younger Dryas. They experienced the sudden cooling, adapted to the return of near-glacial conditions, then adapted again when warmth returned just as quickly. Archaeological evidence shows they adjusted their hunting strategies, migration patterns, and technologies to cope with these rapid changes. This adaptability was crucial because the end of the Ice Age brought enormous changes to human life. As ice sheets retreated and sea levels rose, coastlines shifted dramatically. Land bridges that had connected continents for thousands of years were submerged. Islands appeared where there had been plains. River valleys were flooded, becoming bays and estuaries. The megafauna that humans had hunted for tens of thousands of years started going extinct. Mammoths, mastodons, giant ground sloths, saber-toothed cats, one by one, these animals disappeared. The extinctions were concentrated at the end of the Ice Age, particularly in the Americas, where large mammals were hit hardest. What caused the megafauna extinctions? This is still debated. Climate change certainly played a role. As the planet warmed, the mammoth steppe ecosystem collapsed. The cold-adapted grasslands were replaced by forests and wetlands. Animals specifically adapted to Ice Age conditions struggled in the new environment, but humans probably contributed significantly. As human populations grew and hunting technologies improved, humans put increased pressure on megafauna populations. Animals that had survived multiple Ice Age cycles suddenly faced a new and efficient predator. The combination of climate change and human hunting likely drove many species to extinction. The loss of megafauna transformed ecosystems worldwide. Without mammoths and other large herbivores, vegetation patterns changed. Forests expanded in areas that had been maintained as grassland by grazing. Fire regimes shifted. Predator populations collapsed when their prey disappeared. Humans had to adapt to these new conditions. They shifted from hunting large game to hunting smaller animals, fishing and gathering more plant foods. These changes are visible in the archaeological record. Toolkits change, hunting strategies evolve, evidence of fishing and plant processing increases. And in some regions, humans began experimenting with a revolutionary new strategy for obtaining food. Instead of just hunting and gathering wild resources, they started deliberately cultivating plants and managing animal populations. Agriculture was born. The development of agriculture around 10,000 to 12,000 years ago, during the early Holocene, was directly related to the end of the Ice Age and the beginning of stable interglacial conditions. You can't practice agriculture successfully with a wildly fluctuating climate. You need predictable seasons, reliable rainfall, and stable temperatures. The Holocene provided that stability for the first time in tens of thousands of years. The climate variations during the Holocene have been relatively minor compared to the dramatic swings of the last Ice Age. Temperatures have fluctuated by a few degrees, rainfall patterns have shifted somewhat, but nothing like the abrupt climate changes of the glacial period. This stability allowed agriculture to develop and flourish. Once humans started farming, population densities could increase dramatically. Farming supports far more people per square mile than hunting and gathering. Villages grew into towns, towns grew into cities, complex societies emerged. Civilization as we know it is a product of Holocene stability. Everything we think of as recorded history, from ancient Mesopotamia and Egypt to modern times, all occurred during this relatively stable climatic period. But here's the uncomfortable truth. The Holocene is temporary. It's an interglacial period, just like previous interglacials that eventually ended when orbital cycles shifted and ice sheets began growing again. Based on the pattern of the past 800,000 years, interglacials typically last 10,000 to 15,000 years. The Holocene began 11,700 years ago. By natural cycles alone, we should be approaching the end of this warm period. Northern Hemisphere summer insolation has been declining for thousands of years. Orbital parameters are slowly shifting toward configurations that favor ice sheet growth. Some climate scientists studying natural cycles believe we were actually overdue for the next glaciation to begin. Small ice sheets should have started forming in Canada and Scandinavia centuries ago, growing slowly as snow accumulated faster than it melted. But that hasn't happened. In fact, the opposite is occurring. Mountain glaciers worldwide are retreating. The Greenland ice sheet is losing mass. Summer sea ice in the Arctic is declining. Instead of cooling toward the next ice age, we're warming rapidly. The reason, of course, is human activity. By burning fossil fuels and adding massive amounts of CO2 to the atmosphere, we've created a greenhouse effect strong enough to overwhelm the natural orbital forcing toward glaciation. In a sense, we've postponed the next ice age. Some climate models suggest we may have delayed it by 50,000 years or more. If atmospheric CO2 remains elevated, ice sheets won't be able to grow even when orbital cycles favor glaciation. The planet will stay in an interglacial or super interglacial state for tens of thousands of years. Is this good or bad? From one perspective, preventing an ice age might seem beneficial. Ice ages make much of the northern hemisphere uninhabitable. Sea levels drop, but only because water is locked in ice sheets. The available habitable land doesn't increase, it just shifts around, and the climate becomes more unstable, prone to abrupt changes. But the problem is, we're not just preventing the next ice age, we're warming the planet far beyond natural interglacial temperatures. We're heading toward conditions Earth hasn't experienced in millions of years, and we're getting there at a speed unprecedented in the geological record. The warming we're causing isn't a gentle prevention of ice age cooling, it's a drastic and rapid shift in the opposite direction, pushing temperatures higher than they've been since long before the 100,000 year cycles began. To understand why this matters, we need to look at how much warming is actually required to prevent an ice age versus how much warming we're likely to cause if we continue current trends. Climate models suggest that maintaining atmospheric CO2 at around 300 to 350 parts per million would probably be sufficient to delay the next glaciation. This is only slightly above the natural interglacial level of 280 parts per million. The additional greenhouse effect would offset the cooling from declining summer insolation, keeping temperatures high enough to prevent ice sheet growth. But current CO2 levels are already over 420 parts per million and rising rapidly. If we continue on our current trajectory, we could reach 500 to 600 parts per million by the end of this century, with potential to go even higher if we don't dramatically reduce emissions. At these levels, we're not just preventing ice ages, we're recreating climate conditions from the Pliocene epoch, 3 to 5 million years ago, when Earth was dramatically warmer than today. During the Pliocene, global temperatures were 2 to 3 degrees Celsius warmer than pre-industrial levels, similar to what we might reach this century. but the Pliocene climate took millions of years to develop and stabilize. All of Earth's systems, ice sheets, ocean circulation, ecosystems, vegetation patterns had time to gradually adjust to the warm conditions. We're forcing similar temperature changes in just 1 or 2 centuries, giving Earth systems no time to gradually adjust. This rapid, forced warming causes disruptions that wouldn't occur if warming happened gradually. Ice sheets lose mass faster than they would naturally. Species can't migrate quickly enough to track shifting climate zones. Ecosystems struggle to adapt. Infrastructure built for current climate conditions becomes maladapted to new conditions. The consequences include rising sea levels that threaten coastal cities, changing precipitation patterns that affect agriculture and water resources, more intense heat waves and storms, shifting disease patterns, ecosystem disruptions, and species extinctions. These aren't hypothetical future problems. They're already happening. We're seeing them in real time. And they're occurring even though we've only warmed the planet about 1.1 degrees Celsius above pre-industrial levels. If we continue to 2 to 3 degrees Celsius or more, the impacts will intensify dramatically. So while we may have technically prevented the next ice age, we've done so by causing a different kind of climate disruption that may ultimately be even more challenging for human civilization than an ice age would have been. This brings us to a fundamental question about the 100,000-year cycle and humanity's place in it. Are we just another component of Earth's climate system like ice sheets or ocean currents? Or have we become something different, a force capable of disrupting the natural cycles that have governed climate for millions of years? The geological record shows that Earth's climate system has multiple stable states and can shift between them given sufficient forcing. The transition from ice-free greenhouse world to ice age cycles 2.6 million years ago was one such shift. The mid-Pleistocene transition from 41,000-year to 100,000-year cycles was another. Human activities are now forcing another transition from regular ice age cycles to a new state that may persist for thousands or even millions of years, depending on how long elevated CO2 levels remain in the atmosphere. This isn't necessarily permanent. Over very long timescales, hundreds of thousands to millions of years, natural processes will eventually remove the excess CO2 from the atmosphere. Chemical weathering of rocks consumes CO2. Ocean chemistry adjusts. The carbon cycle rebalances. Eventually, perhaps 500,000 years from now, perhaps longer, atmospheric CO2 might decline back to levels where ice age cycles could resume. Earth might return to the pattern of alternating glacials and interglacials driven by orbital variations. But for the foreseeable future of human civilization, for thousands of years at minimum, we've disrupted the natural cycle. We're conducting an unprecedented experiment with our planet's climate system, taking it into territory that hasn't been explored in millions of years. Understanding the 100,000-year cycle helps us appreciate the magnitude of what we're doing. This isn't just another change in a constantly changing climate. This is disruption of a fundamental planetary rhythm that has operated for millions of years through the entire evolution of modern humans, through all of recorded history and prehistory. Our ancestors adapted to this cycle. They migrated with shifting ice sheets. They adjusted to changing sea levels. They survived abrupt climate shifts during deglaciations. They developed the flexibility and resilience that allowed them to thrive through multiple complete ice age cycles. Now we face a different challenge. Not adapting to natural climate cycles, but managing the consequences of disrupting those cycles ourselves. It's a test of whether the adaptability and intelligence we developed during ice ages can help us navigate the climate crisis we've created. The 100,000-year cycle teaches us that Earth's climate is always changing, that dramatic shifts are possible, that feedback loops can amplify small changes into large ones. These lessons are directly applicable to understanding current climate change. But the cycle also teaches us about timescales. Natural ice age cycles operate over tens of thousands of years. The changes we're causing are happening in decades to centuries. The speed difference is crucial. Natural climate changes, even abrupt ones like the Younger Dryas, occur over timescales that allow some adaptation. Species can migrate. Ecosystems can adjust gradually. Humans can modify their behavior and technology to cope with new conditions. But when changes happen too quickly, adaptation becomes difficult or impossible. Species can't migrate fast enough. Ecosystems collapse. Infrastructure becomes obsolete. Societies struggle to cope. This is the real danger of anthropogenic climate change. Not that the planet is warming. Earth has been much warmer in the past, but that it's warming so fast that natural systems and human societies can't adapt quickly enough. The 100,000-year cycle has shaped our planet, our biosphere, and our species for millions of years. It's given us ice ages and interglacials, shaped human evolution and migration, created the climate conditions that allowed civilization to develop. Now we're disrupting it, altering the rhythm that has governed Earth for longer than our species has existed. Whether this turns out to be a catastrophic mistake or a successful navigation of a new challenge will depend on the choices we make over the next few decades and centuries. Understanding why Earth freezes every 100,000 years isn't just about satisfying scientific curiosity. It's about understanding the climate system we're disrupting, appreciating the timescales on which natural changes occur, and recognizing the unprecedented nature of the experiment we're conducting. We are living through one of the most significant moments in Earth's climate history. The decisions we make now will reverberate through thousands or millions of years, affecting not just ourselves, but countless future generations and potentially the entire trajectory of life on Earth. That's the real significance of the 100,000-year cycle. It's not just a fascinating scientific discovery. It's a window into Earth's climate past, a context for understanding our present, and a warning about our future. The ice will return someday, assuming we don't prevent it permanently, or it won't if we keep CO2 levels elevated indefinitely. Either way, humanity has become a geological force, capable of altering planetary processes that operate on timescales far longer than civilizations or species. That's both an awesome power and an enormous responsibility. And understanding the natural cycles we're disrupting is the first step toward using that power wisely. The story of why Earth freezes every 100,000 years is ultimately the story of our planet as a dynamic, interconnected system where small changes can cascade into large effects, where astronomical cycles shape biological evolution, where ice and ocean and atmosphere and life all interact in complex ways. It's a story that's still being written, Scientists continue to refine our understanding of ice age cycles, discovering new feedbacks and mechanisms, developing better climate models, extracting new evidence from ice cores and sediments. And it's a story we're now part of, not just as observers studying the past, but as participants shaping the future. The next chapter of Earth's climate history will be written by us, by the choices we make, by whether we continue disrupting natural cycles or find ways to work within them. The 100,000-year rhythm that has dominated Earth's climate for millions of years is changing, and we're the reason why. What happens next is up to us. But there's another layer to this story that we need to explore, something that reveals just how intricate and interconnected Earth's climate system really is, because the 100,000-year cycle doesn't operate in isolation. It's embedded in a complex web of other cycles, feedback mechanisms, and planetary processes that all interact in ways scientists are still working to fully understand. Let's start by looking more closely at the other orbital cycles that Milankovitch identified, because they don't just disappear when the 100,000-year cycle dominates. They're still there, still affecting climate, still leaving their signatures in the geological record. The 41,000-year axial tilt cycle continues throughout the Quaternary Ice Age. Earth's axis wobbles between 22.1 and 24.5 degrees of tilt, and this variation affects the intensity of seasons in both hemispheres. When the tilt is at its maximum around 24.5 degrees, summers are hotter and winters are colder because each hemisphere is tilted more dramatically toward and away from the sun during its respective season. When the tilt is at its minimum, around 22.1 degrees, seasons are more moderate. Summers are cooler, winters are warmer, because the hemispheres aren't tilted as much relative to the sun's rays. This moderation of seasons affects ice sheet growth in subtle but important ways. During periods of minimum tilt, high-latitude summers are cooler, which you might think would favour ice growth, and it does to some extent. But minimum tilt also means winters aren't as cold, which can reduce snowfall in some regions. The relationship between tilt and ice sheet growth is complex and varies by location. The tilt cycle shows up clearly in climate records. When scientists analyze ice cores or ocean sediments, they can see variations that occur on a 41,000-year timescale. These variations are superimposed on top of the dominant 100,000-year cycle, creating a complex pattern of climate fluctuations. Then there's the precession cycle, which has a period of about 23,000 years. Precession is even more subtle than the tilt cycle in its effects, but it's still important. Remember that precession determines which hemisphere is tilted toward the sun during different parts of Earth's orbit. Currently, Earth is closest to the sun in early January during Northern Hemisphere winter. This means northern winters are actually slightly milder than they would be if we were farthest from the sun in January. Southern summers, meanwhile, are slightly more intense because the southern hemisphere is tilted toward the sun when Earth is closest to it. But 11,500 years from now, due to precession, the situation will be reversed. Earth will be closest to the sun in July during northern hemisphere summer. This will make northern summers slightly more intense and northern winters slightly harsher. Southern seasons will moderate in the opposite way. These precession-driven changes in seasonal intensity affect ice sheet growth, particularly when combined with the eccentricity cycle. Remember that eccentricity determines how elliptical Earth's orbit is. When eccentricity is high, meaning the orbit is more elliptical, the difference between Earth's closest and farthest approach to the Sun is greater. This amplifies the effects of precession. If you have high eccentricity and precession puts Northern Hemisphere summer when Earth is closest to the Sun, you get very intense northern summers. Lots of ice melting. But if precession puts Northern Hemisphere summer when Earth is farthest from the Sun during a period of high eccentricity, you get very weak northern summers, minimal ice melting, perfect conditions for ice sheet growth. This interaction between eccentricity and precession creates complex patterns in the climate record. Sometimes the 100,000-year cycle dominates. Sometimes the 41,000-year cycle is more prominent. Sometimes the 23,000-year cycle shows up clearly. And sometimes all three cycles combine to create climate changes that are greater than any single cycle would produce alone. Climate scientists call this the pacing problem. The orbital cycles are relatively simple and well understood. We can calculate Earth's orbital parameters for millions of years into the past and future with high precision. But predicting exactly how the climate will respond to these orbital forcings is much more difficult because of the complex interactions between different cycles and the various feedback mechanisms in the climate system. One of the most puzzling aspects of the 100,000-year cycle is that it's actually the weakest of the three orbital forcings in terms of direct effect on solar radiation reaching Earth. The changes in incoming sunlight caused by eccentricity variations are tiny, much smaller than the changes caused by tilt or precession variations. Yet somehow, the eccentricity cycle dominates the climate response during the past million years. The major glaciations follow the 100,000-year rhythm, not the 41,000 or 23,000-year rhythms, even though those cycles have stronger direct effects on sunlight distribution. This paradox has puzzled scientists for decades. How can the weakest orbital forcing produce the strongest climate response? The answer lies in the feedback mechanisms we discussed earlier, particularly carbon dioxide changes and ice sheet dynamics, but the details are still being worked out. One theory suggests that the 100,000-year cycle emerges because ice sheets have internal dynamics that naturally produce long growth and short decay cycles. Ice sheets grow slowly because snow has to accumulate year after year for thousands of years, but they can melt relatively quickly once certain thresholds are crossed. This asymmetry between slow growth and rapid decay could naturally produce a cycle where ice sheets spend most of their time growing or at maximum extent, with relatively brief periods of rapid melting. If the internal dynamics of ice sheets naturally produce cycles around 80,000 to 120,000 years, then even weak forcing from orbital eccentricity might be enough to trigger and pace these cycles. Another theory focuses on the carbon cycle. Remember that atmospheric CO2 drops during glacial periods and rises during interglacials. These CO2 changes amplify the initial orbital forcing. But what if the carbon cycle itself has dynamics that naturally operate on 100,000-year timescales? Some researchers have proposed that carbon gets stored in the deep ocean during glacial periods through complex interactions between ocean circulation, biological productivity, and chemical processes. This carbon storage might have natural timescales related to ocean mixing rates that happen to match the 100,000-year eccentricity cycle. If the carbon cycle and the eccentricity cycle are naturally resonant, meaning they operate on similar timescales, then even weak eccentricity forcing could trigger large carbon cycle responses, which would then drive major climate changes. A third theory involves marine ice sheets, particularly the Antarctic ice sheet. Unlike the Northern Hemisphere ice sheets that grew on land, parts of the Antarctic ice sheet rest on bedrock that's below sea level. These marine-based ice sheets have unique dynamics that can make them unstable. When a marine ice sheet retreats, warm ocean water can get underneath it, causing rapid melting from below. This can trigger runaway collapse, where the ice sheet rapidly loses mass. Some scientists think these marine ice sheet instabilities might have natural timescales around 100,000 years, and that Antarctic ice sheet collapse might be what actually terminates glacial periods. The truth is probably some combination of all these factors. The climate system is complex enough that multiple mechanisms can interact and reinforce each other. Ice sheet dynamics, carbon cycle variations, ocean circulation changes, and orbital forcing all work together to produce the 100,000-year cycle we observe in the geological record. What's fascinating is that scientists are still discovering new aspects of this cycle. In recent years, researchers have found evidence for even longer cycles in Earth's climate. There's a roughly 400,000-year cycle that modulates the 100,000-year cycle, making some ice ages more severe than others. There are hints of million-year cycles related to patterns in Earth's orbital eccentricity. These ultra-long cycles suggest that Earth's climate system operates on multiple timescales simultaneously, from decades to millions of years. Understanding how all these different timescales interact is one of the great challenges of modern climate science. But let's zoom back in to the 100,000-year cycle and explore what actually happens to different parts of the planet during a complete cycle. Because while we've talked about global changes, the regional variations are equally important and fascinating. Start with the North Atlantic, which is ground zero for Ice Age dynamics in many ways. This is where some of the largest ice sheets form during glacial periods. It's also where ocean circulation changes have their most dramatic effects, and it's one of the regions that experiences the most extreme temperature swings during glacial interglacial transitions. During glacial periods, the Laurentide ice sheet covers most of Canada and extends deep into the northern United States. At its maximum extent, it reaches as far south as New York, Pennsylvania, and even parts of Kentucky. The ice is miles thick over Hudson Bay, depressing the crust hundreds of feet. Along the southern margin of the ice sheet, a zone of tundra extends for hundreds of miles. This isn't the lush tundra of Alaska today. It's a colder, harsher landscape with sparse vegetation, frequent dust storms, and permafrost extending deep into the ground. Summers are brief and cool, winters are long and brutally cold. South of the tundra, boreal forests exist, but in a configuration different from today. Spruce trees that now grow in Canada are found in Tennessee and North Carolina. Species that don't grow together today are mixed in unique combinations. The forests are more open, more like parkland than the dense forests of today. The Atlantic Ocean itself is dramatically different. Sea surface temperatures drop by several degrees. The warm Gulf Stream weakens or shifts position, reducing heat transport to Europe. Parts of the North Atlantic that are now ice-free year-round have seasonal or even year-round sea ice. The formation of sea ice affects ocean salinity and density, which drives deep water formation. During glacial periods, the location and intensity of deep water formation can change dramatically. Sometimes it shuts down completely, as happened during Heinrich events when massive armadas of icebergs flooded the North Atlantic with fresh water. Europe, deprived of the warming influence of the Gulf Stream and blocked by ice sheets to the north, becomes much colder and drier. Temperatures drop 10 to 15 degrees Celsius or more. Forests retreat to southern refugia in Spain, Italy, and the Balkans. Most of the continent is tundra or cold steppe. The changes in Europe are dramatic enough that they fundamentally altered human prehistory. During glacial maxima, much of Europe was uninhabitable. Human populations retreated to southern refugia, then expanded northward again during warmer periods. This repeated expansion and contraction shaped the genetic structure of European populations. Archaeological sites show that humans abandoned regions during glacial advances and recolonized them during retreats. The earliest human settlement of Britain, for instance, was repeatedly established and then abandoned as ice sheets advanced and retreated. Modern British populations descend from people who recolonized the island after the last ice age ended, not from earlier groups who were forced out by advancing ice. The Mediterranean region, while much colder than today, remained relatively habitable during glacial periods. It served as a refugium for both humans and many other species. Forests persisted in protected valleys. Some coastal areas remained ice-free and supported diverse ecosystems. But the Mediterranean itself was different. Lower sea levels exposed parts of the continental shelf. Some islands were connected to the mainland. The climate was cooler and generally drier, though some areas received more rainfall than today due to shifts in storm tracks. North Africa and the Middle East went through dramatic changes. The Sahara Desert expanded and contracted repeatedly during glacial cycles. At times, it was even more arid than today, an almost lifeless expanse of sand and rock. At other times, shifts in the monsoon brought more rainfall and the Sahara became grassland dotted with lakes and supporting diverse wildlife. These climate fluctuations in North Africa had profound effects on human populations. During wet periods, humans spread across the Sahara, leaving archaeological sites and rock art that testify to their presence. During dry periods, populations contracted to oases and river valleys. The Arabian Peninsula went through similar cycles. During some glacial periods, it was a harsh desert that was largely uninhabitable. During other periods, increased rainfall created rivers, lakes, and grasslands that supported human and animal populations. Some researchers think humans migrated out of Africa through Arabia during wet periods when it was habitable. East Africa, the cradle of human evolution, also experienced dramatic climate changes during glacial cycles. The Great Lakes of the East African Rift Valley, like Victoria, Tanganyika, and Malawi, expanded and contracted dramatically. During the driest periods, some lakes dried up completely or were reduced to small remnants. The vegetation belts on mountains like Kilimanjaro and Mount Kenya shifted vertically by thousands of feet. During glacial periods, alpine vegetation extended far down the mountains. Forests retreated to lower elevations. The overall landscape was more open, with more grassland and less forest than today. These environmental changes created selection pressures on early humans. access to water became more critical. Finding food required greater mobility and flexibility. The ability to exploit diverse resources and adapt to changing conditions was crucial for survival. Some researchers believe that the climate instability of the last few million years, driven by glacial interglacial cycles, was a major factor in human brain evolution. The environmental challenges forced humans to become more intelligent, more adaptable, more capable of complex planning and problem solving. In a stable environment, there's less pressure to evolve greater intelligence. In a rapidly changing environment, intelligence becomes crucial for survival. Moving to Asia, the effects of glacial cycles were equally dramatic, but different in detail. The Himalayas and Tibetan Plateau developed much more extensive glaciation during glacial periods. Glaciers extended far down mountain valleys. The plateau itself was colder and even more arid than today. These changes affected the monsoon system that brings rainfall to much of Asia. During glacial periods, the monsoon was generally weaker. Less moisture reached interior Asia. Deserts expanded. The Gobi Desert was larger. Central Asian steppes extended over areas that are now more vegetated, but the effects varied by region and by which orbital configuration drove each particular glaciation. Some glacial periods brought more moisture to certain parts of Asia, even as other parts became drier. The patterns were complex and didn't follow simple rules. Southeast Asia underwent perhaps the most dramatic geographical changes. The Sunda Shelf, a vast area that's now submerged under shallow seas, was exposed during glacial periods when sea level dropped. Malaysia, Sumatra, Java, and Borneo were connected into a single landmass called Sundaland. This exposed shelf wasn't just featureless mudflat, it was a complex landscape with rivers, forests, and diverse ecosystems. Large river systems drained the interior of Sundaland, flowing hundreds of miles before reaching the ocean. These rivers supported riparian forests and wetlands that were home to diverse wildlife. Humans colonized Sundaland during glacial periods, spreading across what are now separate islands. When sea levels rose during deglaciation, human populations were stranded on newly formed islands. This isolation led to genetic and cultural divergence, contributing to the incredible linguistic and genetic diversity of modern Southeast Asian and Pacific populations. Australia, connected to New Guinea and Tasmania in the supercontinent of Sahul, was also dramatically different during glacial periods. The interior was even more arid than today. Many of the ephemeral lakes that sometimes fill with water after rare rains were completely dry for thousands of years. But the coastal areas, including the now submerged continental shelf, had more diverse ecosystems. Rivers flowing from the interior crossed the exposed shelf before reaching the ocean. These river systems created corridors of relatively productive habitat through otherwise harsh landscapes. Aboriginal Australians adapted to glacial conditions by developing sophisticated water management strategies, knowledge of drought-resistant plants, and social systems that allowed resource sharing across vast territories. Their survival strategies during glacial periods were so effective that they maintained continuous occupation of the continent for over 50,000 years through multiple climate cycles. The Pacific Islands present a different story. During glacial periods with lower sea levels, some islands were larger or connected to each other, but the deep ocean trenches that separate island groups were never exposed. the Pacific remained a formidable barrier to human migration throughout glacial cycles. The colonization of the remote Pacific Islands by Polynesians is actually a relatively recent event, occurring during the current interglacial period over the past few thousand years. It required sophisticated boat building and navigation technologies that allowed humans to cross vast stretches of open ocean. South America experienced complex regional variations during glacial cycles. The Andes developed much more extensive glaciation. Glaciers extended far down valleys, and in some places reached lowland areas. The Amazon basin's climate remains controversial, with some evidence suggesting it remained mostly forested, and other evidence suggesting it fragmented into smaller forest patches separated by grassland. The Patagonian region of southern South America became much colder and windier. The westerly wind belt strengthened and shifted position, bringing changes in precipitation patterns. The southern tip of the continent may have been connected to Antarctica by a land bridge during the most extreme glacial periods, though this remains debated. North America south of the ice sheets went through dramatic changes. The Great Plains were much colder and windier. Massive herds of grazing animals, mammoths, bison, horses, camels, roamed across vast grasslands. These herds supported predator populations that included saber-toothed cats, American lions, dire wolves, and eventually human hunters. The southwestern United States, which is now mostly desert, had a very different climate during parts of the last ice age. Pluvial lakes, formed by increased rainfall or decreased evaporation, covered areas that are now dry. Lake Bonneville, which covered much of western Utah, was as large as Lake Michigan. Lake Lahontan in Nevada was similarly huge. These lakes supported diverse ecosystems and provided water and resources for human populations. Archaeological sites around these ancient lakes show that humans took advantage of the resources they provided, hunting waterfowl, fishing, and gathering plant foods along the shorelines. As the Ice Age ended and climate warmed, these pluvial lakes dried up. The Great Salt Lake in Utah is a small remnant of the much larger Lake Bonneville. The dry lake beds across Nevada and Utah are remnants of once extensive water bodies. The drying of these lakes had profound effects on human populations in the region. Groups that had relied on lake resources had to adapt to new conditions, developing desert survival strategies or migrating to areas with more reliable water sources. All of these regional changes during glacial cycles had one thing in common. They were dramatic. They affected every aspect of the environment, and they happened repeatedly as Earth cycled through glacial and interglacial periods every 100,000 years. Species that couldn't adapt went extinct. Species that could adapt, including humans, survived and sometimes thrived despite the challenges. The ability to handle climate change, to adjust strategies when environments shifted, became one of the most important survival traits for any organism. This brings us to an important question about the future. If glacial cycles have been such a powerful force shaping ecosystems and evolution for millions of years, what happens when we disrupt those cycles? What are the consequences for species and ecosystems that have adapted to regular climate fluctuations? Many species have evolved strategies specifically tuned to glacial interglacial cycles. They track shifting climate zones by migrating as temperatures change. They have physiological adaptations that allow them to tolerate a range of conditions. They have life history strategies that allow them to persist through unfavorable periods. But these adaptations assume that climate changes occur on timescales of thousands to tens of thousands of years. They assume species have time to migrate, to adjust, to evolve if necessary. What happens when climate changes in just decades or centuries instead? Many species can't migrate fast enough to track the climate zones they're adapted to. Plants in particular migrate slowly, limited by seed dispersal distances and the time it takes for new populations to establish. If climate zones shift faster than plants can migrate, species get left behind in environments they're no longer well adapted to. Animals can migrate faster than plants, but they're often dependent on specific plant communities or ecosystem types. If the ecosystems they depend on are disrupted, animals suffer even if they could physically migrate fast enough. Marine species face similar challenges. Ocean temperatures and chemistry are changing rapidly. Species adapted to specific temperature ranges or pH levels are finding their habitat shrinking or shifting faster than they can track it. Coral reefs in particular are extremely sensitive to temperature changes and are being devastated by warming oceans. The rapidity of current climate change is unprecedented in the context of the 100,000-year cycle. Even the fastest natural climate changes, like the termination of the Younger Dryas, occurred over decades to centuries and affected mainly regional climate, not the entire globe simultaneously. What we're doing now is warming the entire planet simultaneously in just decades, creating climate conditions that haven't existed for millions of years. Species haven't encountered these conditions within their evolutionary memory. They don't have adaptations ready for these new circumstances. This is why current extinction rates are alarming. We're losing species at rates that rival or exceed the great mass extinctions of the geological past. And we're doing it not through asteroid impacts or massive volcanism, but through rapid climate change combined with habitat destruction, pollution, and other human impacts. The 100,000-year cycle has shaped biodiversity by creating repeated opportunities for species to adapt, migrate, and diversify. The cycles created refugia where species could persist during unfavorable periods, then expand again when conditions improved. They created isolation that led to speciation, then reconnection that allowed genetic mixing. By disrupting this cycle, we're not just changing climate, we're altering the fundamental processes that have shaped the evolution and distribution of life on Earth for millions of years. The consequences will play out over centuries and millennia as ecosystems struggle to adjust to new conditions and species either adapt or go extinct. Some species will likely benefit from warming. Those adapted to warm conditions might expand their ranges. Some agricultural regions might become more productive. New ecosystems might emerge combining species in novel ways. But the transition period will be challenging. Ecosystems in flux are often less productive and less stable than stable ecosystems. Species communities take time to reassemble into functioning systems. During the transition, we're likely to see widespread ecosystem disruption with consequences for everything from food production to disease outbreaks to natural disaster frequency. All of this connects back to the 100,000-year cycle because that cycle provides the baseline for understanding natural climate variability. It shows us how climate has changed in the past, how species and ecosystems ecosystems have responded, and what happens during rapid climate transitions. The deglaciation that ended the last ice age is our best analogue for current climate change. It shows us what happens when climate warms rapidly, when ice sheets melt, when sea levels rise, when ecosystems shift. But even that analogue is imperfect because the last deglaciation occurred over 10,000 to 15,000 years, giving species more time to adjust than they have now. Understanding the mechanisms behind the 100,000-year cycle also helps us predict future climate. Climate models that successfully reproduce past glacial cycles give us more confidence in their predictions for the future. By testing models against the geological record, scientists can refine them and identify which processes are most important for determining climate. This is why paleoclimate research, the study of past climate from geological evidence, is so valuable. It's not just about satisfying curiosity about the past. It's about understanding the climate system well enough to predict the future and make informed decisions about how to respond to the changes we're causing. The ice cores extracted from Antarctica and Greenland are particularly valuable for this research. These cores contain annual layers of ice going back hundreds of thousands of years. Each layer preserves information about temperature, atmospheric composition, dust levels, and other climate variables. By analysing these ice cores, scientists have reconstructed a detailed history of climate and atmospheric CO2 covering the past 800,000 years. This record shows the regular oscillation between glacial and interglacial periods, the tight relationship between temperature and CO2, and the abrupt climate changes that punctuated glacial periods. The ice core record also provides context for understanding current CO2 levels. For the entire 800,000 years covered by ice cores, atmospheric CO2 never exceeded 300 parts per million until the industrial era. The natural range was between about 180 parts per million during glacials and 280 parts per million during interglacials. Current CO2 levels over 420 parts per million are completely unprecedented in this entire record. To find comparable CO2 levels, you have to go back millions of years to periods when Earth was much warmer and sea levels were much higher than today. This is why climate scientists are concerned. We're not just changing climate within the range of natural variability. We're pushing the climate system far outside the range it has experienced throughout the entire period when ice age cycles have operated, throughout the entire evolutionary history of modern humans. Ocean sediment cores provide even longer climate records going back tens of millions of years. These cores show that ice age cycles are actually a relatively recent phenomenon in Earth's history. For most of the past 65 million years since the dinosaurs went extinct, Earth was much warmer than today, with little or no permanent ice. The transition to an ice age state occurred gradually over tens of millions of years as the planet slowly cooled. Antarctica developed ice sheets about 34 million years ago. The Northern Hemisphere didn't develop major ice sheets until about 2.6 million years ago, initiating the Quaternary Ice Age we're still in today. This long-term cooling trend was driven by gradually declining atmospheric CO2 levels, which were controlled by the balance between volcanic outgassing and removal through rock weathering and ocean chemistry. The cooling eventually reached a threshold where ice age cycles became possible, with orbital variations pacing the growth and decay of ice sheets, but Earth could could return to an ice-free state if CO2 levels remain elevated long enough. The planet has been there before and could go there again. Whether that happens depends entirely on human actions over the next few centuries. Some climate scenarios project that if we burn all available fossil fuels, atmospheric CO2 could reach 1,000 parts per million or higher. At these levels, Earth would likely transition to a hot greenhouse state similar to the Eocene 50 million years ago, when there was no permanent ice anywhere and sea levels were 200 feet higher than today. That transition wouldn't happen immediately. Ice sheets take centuries to millennia to fully melt. Climate takes time to fully adjust to new CO2 levels, but the transition would be inevitable if CO2 levels remained elevated long enough. Alternatively, if we dramatically reduce emissions and eventually remove CO2 from the atmosphere, climate might eventually return to conditions where ice age cycles could resume. But this would take thousands of years at minimum, and the climate system might not return to exactly the same state it was in before we disrupted it. The Earth system has multiple potential stable states, and which one it settles into depends on a complex set of factors. It's possible that anthropogenic climate change could push Earth into a new stable state that persists for millions of years, fundamentally altering the planet's climate trajectory. This is the awesome responsibility we face. Our actions over just a few centuries will determine Earth's climate for thousands or millions of years into the future. We're not just affecting ourselves or our immediate descendants. We're potentially affecting the entire future evolution of Earth's climate system and biosphere. The 100,000-year cycle has been one of Earth's fundamental rhythms for 2.6 million years. It has shaped continents, oceans, ecosystems, and the evolution of our own species. Now we're disrupting it, ending a pattern that has persisted through the entire existence of the Homo genus, through all of human evolution and prehistory. Whether this disruption leads to catastrophe or to successful navigation of a new climate regime depends on how we respond. Do we continue on our current trajectory, pushing CO2 levels to heights not seen in tens of millions of years? Or do we change course, limiting warming and eventually allowing the climate system to return toward more natural conditions? These aren't just scientific questions. They're moral and political questions that will define our legacy as a species. Future generations, if they exist, will look back on this period as the time when humanity either rose to meet the greatest challenge it had ever faced or failed to act when action was still possible. The ice cores and ocean sediments and geological formations that record Earth's climate history will also record what we did. They'll preserve the geochemical signature of fossil fuel burning, the isotopic evidence of anthropogenic CO2 emissions, the sudden warming trend that broke the 100,000-year cycle. In a very real sense, we're writing a new chapter in Earth's geological history. The Anthropocene, as some scientists call it, the age when humans became a planetary force. Whether that chapter records wisdom and foresight or short-sighted destruction remains to be determined. Understanding why Earth freezes every 100,000 years gives us the context to appreciate what we're doing and what's at stake. It shows us that climate change is real, that it's powerful, that it affects everything. but it also shows us that climate can be stable for long periods, that human civilization has benefited from Holocene stability, and that disrupting that stability carries enormous risks. The cycle will continue unless we prevent it. The ice will return unless we stop it. And the question facing humanity is not whether we can affect Earth's climate. We already know we can, but whether we will use that power wisely or carelessly. The answer to that question will reverberate through geological time, affecting Earth and life on it for longer than we can easily imagine. And it all connects back to those orbital cycles that Milankovitch calculated, to the ice sheets that Agassiz studied, to the climate records extracted from ice and ocean sediments by modern scientists. The story of why Earth freezes every 100,000 years is ultimately a story about us, about how we came to understand our planet's past, about the climate system that shaped our evolution, and about the future we're creating through our actions. It's a story that's still being written, and we're all authors of the next chapter. The Ice Age cycle has governed Earth for millions of years. What we do now will determine whether it continues for millions more or ends permanently, replaced by something entirely different. That's the real significance of the 100,000-year cycle, not just as a scientific curiosity, but as a lens for understanding our planet, our past, and our responsibility for the future. Earth has been freezing and thawing in this regular rhythm for longer than our species has existed. And now, for the first time in millions of years, that ancient rhythm is breaking down because of us. What comes next is up to us to decide.